All right.
Put up or shut up.
Okay, so are we ready for 440? Sort of, maybe. Okay.
Stop talking about
We're never ready for 440. I understand. All right, so what we'll do today is I do have a new homework assignment as promised. And it is related to discrete probability distribution. And it's something that we haven't seen before. Well, sort of. We've seen a little bit of that before, but not exactly this problem. But I think you guys can probably work this one out, and it's kind of fun to work this one out, I think. So let's take a look. It's called Circles and Sequences. I think some people might have a chance to read this before class. So the problem is, we have n people sitting in a circle, okay? So you have, just, a certain number of people, say A, B, C, D, E, F. So these are people sitting in a circle. And then we have 1 to n numbers to distribute. So in this case, we have 1, 2, 3, 4, 5, 6 as numbers, and each person can take one of those numbers. Okay? Non-repeating, so without duplication. So one way to assign the numbers is 1, 2, 3, 4, 5, and then 6 like this. This is one way to assign the numbers. The question is, what are the chances at least r people, r is a number, sitting next to each other get numbers that are in a sequence? So in this case, we have the longest sequence is 4, 5, 6, which is a sequence of 3 numbers. So when r is 3, then we have exactly 1 occurrence. But at the same time, because I'm only asking, what are the chances at least r people are sitting next to each other has numbers that are in the sequence. You can also say 1 because 2, 4, 5, 5, 6, they're both 2. So you have to remember the phrase at least, which is this part here. Yep.
So would 2, 3 count, like C, then D?
It would meet that requirement, yes. So this particular configuration will meet the requirement of r being 2 as well as r being 3. So are there any questions about what I mean by r people sitting next to each other having numbers that are in the sequence? Now remember, this is also a circle, so as far as the people are concerned, there's no beginning and no end. It's not on the straight line.
Is the sequence always in ascending order? Like, is there a direction to the sequence?
It did not specify the ordering, which means it can be ascending or it can be descending order. Okay. Yep.
If you stick with ascending, if you choose ascending, you have to stick with ascending, or can you go either way? So like, if we look at E, F, that's 5, 6. I think we also count C, D, which is 2, 3.
Yes.
So both at the same time in the same occurrence?
Correct.
Okay.
So this one would meet a sequence of 2, several times, because there's one sequence of 2 here between C and B. There's one sequence of 2 between D and E, and there's another sequence of 2 between E and F. But when you're looking at a sequence of 3, there's only one, which is just D, E, F. Okay. Is that okay? All right. So the question is, if I have n people sitting in a circle and I distribute, these numbers to each person in a random way, what are the chances that at least r people, I want an equation, I want a formula that will tell me the chances of r people sitting next to each other getting numbers that are in a sequence. That's basically what that's the main portion of the homework assignment. So the next paragraph talks about how to approach the problem, how to get started with solving this problem. To approach this problem, first think of concrete cases where n is a manageable size so that all possible number assignments can be enumerated, can be listed. Then from the enumerated number assignments, figure out how r is going to affect the chances. Is that okay? Does everybody understand what this is suggesting you to do? Okay, you don't have to do it. I'm not looking for proof that you did it this way. But I think it might be helpful, to basically come up with a small n so that you can enumerate all the possible cases. Now, certain numbers do not work really well. Okay, like 3 doesn't really work well. 2 doesn't work well. So you might want to start with 4. The reason why 3 doesn't work well is because if you only have 3 people and you have 3 numbers, they're always in sequence. There's no way to make 3 numbers out of sequence. It doesn't matter how you write it, it's just a matter of which way you read it. Because you can read this one as 1, 2, 3, which is a sequence of 3. If you write it the other way, that's not the other way, is it?
Mixing it up.
If you tilt your head, it is. Okay, we'll do a mirror image. This is the other way, but it's just the opposite direction. So that means you have to get to at least 4 to really look at all the certain ways to arrange the numbers where you have no sequences, and then you will start to see the pattern. When you get to 5, it will be even better as an example, but the number of ways to arrange the numbers is going to be a lot more, because it's going to be 5 times the number of ways to arrange 4 numbers. This is all factorial related. Is that okay? All right. So let me just ask you a quick question. How many ways can I arrange or assign these numbers when there are n people and n numbers? It will be n factorial, because the first person has n numbers to pick from, the next one has n minus 1, and so on. So it's n factorial. So when you look at 4 factorial, which is 4 times 3 times 2 times 1, it's only 24. But when you look at 5 factorial, it is 5 times 24, which is 120. So which is a little bit out of what you can do by hand anymore. Okay, this one you can do by hand. This one probably not a very good idea to do it by hand. But if you cannot figure out the pattern, because 4 is still a pretty small number for n, what are you going to do? And you want to be able to see everything by just visualize everything first before you try to come up with a formula. What are you going to do? Because 5 already has 120 cases, 6 factorial is 720, which is way too much for anyone to sort out by hand. But this is a computer science class, so what are you going to do? Write a program to do it, which is what the next paragraph is about. So the manual method is only feasible for a fairly small value of n. I would just say up to 4 is okay, but 5 is probably a little bit too much. You can still do it, it's just a little bit too much. As a result, to gain more insight of the solution, you may want to write a program to experiment with larger values of n so that you can see the pattern. Okay? So the way you do it is to use a generate and test method. A generate and test method is one of the oldest classical method in AI or artificial intelligence, which is kind of like a brute force approach. So what you do is you generate all possible number assignments, and then you write a subroutine as a filter to basically say, does it meet this requirement, yes or no? Okay. So from that, from generating and testing and look at the end result, hopefully you can count and start to see a pattern and say, oh, so if n equals to 6 and r equals to 2, there are this many cases that will fit the requirement, and you start to kind of understand how to count those combinations. Is that okay? All right. There are 2 ways to do this, generate and test, okay, at least 2. One is to write a program, a single program, where the first part of the program generates the possible ways to assign numbers, and then the second part of the program is just a little filter to evaluate each assignment to see whether a particular combination meets the requirement or not. Okay, that's one way to do it. The second way to do it is to have a particular program to do the generate and have a different program to do the test. So the generate program is only going to generate the n factorial combinations and spew everything out into an output file. Okay? And then the second program, the test program, is going to take the output of the first program as its input. Then it will go through every single line and figure out, okay, this pattern fits this requirement, this pattern fits this requirement, this one does not, and give you a count. Yep?
Just for clarification, so the test program is going through to figure out how many of those numbers fall into a sequence? That's the test?
Right. So with the case of 4, I can easily enumerate all the possible cases. So in the case of 4, you can basically have 1, 2, 3, 4, 1, 2, 4, 3. But you have to remember it is circular. So the 1 is really next to the 4. And then you have 1, 3, 4, 2, 1, 3, 2, 4, and so on. Is that okay? So you will start to see patterns because some of these are really identical to the other one because remember it's a circle. So the next one up is going to be 1, 4, 2, 3, and then 1, 4, 3, 2. So that should account for all the ones. Yep. The numbers do not wrap around, but the position do. So that means 6, 1 is not considered a sequence because you don't wrap the numbers around. But as far as the people are concerned, the position of the people is concerned, they wrap because it's just a circle. Yep.
The program is just for our personal enrichment, right? That's not part of the assignment?
It is not a part of the assignment, but I think you might find it useful, just to be able to visualize and see, oh, when R is 2, we have this number of cases meeting that requirement. When R is 3, there are this number, and so on. Okay. Are there any questions about the generate and test approach? No questions? Okay. So with this one, we are not done yet because 4 times 3 times 2 times 1 is 24, so I should have 24 cases. But you can probably see how the other cases would look like. The next one is going to be all starting with 2. The next one is all starting with 3. And then the last one is all going to be starting with 4. But you will start to see certain pattern is like, oh, okay, this one is exactly like this one, but with all the numbers rotated by one position. So you will start to recognize patterns. And then when you do the counting, that will help you with how to formulate the actual closed form formula to calculate the likelihood or the chances. Is that okay? All right. So to relate this to the terms or to relate to the formality that we talked about last time, you need to figure out what is omega for a certain number n and the cardinality of omega because that becomes your denominator of your chances. Yep.
Are you recording by any chance?
I sure hope so. Yep, it is recording, but it's good to check. All right. Your answer should be in a journal format where you log and describe how you approach the problem. So every time you work on this, just add something to your log entry. Just kind of say, okay, on a certain date, this is what I'm doing, and okay, it didn't seem to work. It's okay to just log it. Because I just want you to be able to kind of go back in time and figure out, how you think about this problem. Okay, yep, go ahead.
Just to clarify, we have to find the closed form of the omega and then the cardinality of omega too?
Well, the cardinality of omega is really useful because the chances or probability is basically something, the frequency of a particular pattern happening divided by the cardinality of omega itself. And that's why omega is so important, or at least you have to know what is the cardinality of omega, because that's your denominator. The numerator is basically the frequency of the certain combinations that fit your particular requirement. Okay? So are there any questions about this homework assignment? It's kind of open-ended, how you want to approach this problem. You can approach it from the kind of more theoretical, aspect and just kind of think in abstract terms. You can also get, kind of down to earth and write programs and actually see the patterns and then try to formulate the formula, based on your observation. Yep.
So what kind of formula are you looking for?
What kind of?
Yeah, the final solution. What was that
The
gonna
final
look like?
solution is really just a formula. But I want you to kind of indicate how you come up with the formula. What inspired you to kind of know, oh, okay, I think this is the formula. How do you check it? How did you check that the formula is actually correct? So the program is going to be helpful because a program can easily work up to maybe n equals to 7 or possibly 8. because even 8 factorial is something that a computer can handle. It might take a little bit of time, but it's something they can handle. So when you come up with a closed form formula, you can cross-check it with your program and see whether the numbers are the same or not. So from that perspective, having a program to do all the testing actually helps when you want to validate your formula. Is that okay or not?
Sure.
Okay. Yep, George.
But this is more like for if we wanted to go down the path of writing the code. Is there a much more efficient way to do the test cases as opposed to like having some? Because we have to like loop through whatever the series of
Yes.
and so it would be kind of ugly to just go.
Okay, so here's the question. Okay, I think the question that George has is, how do we write and generate and test program? Okay, and particularly, I think your question has to do with the generate part. Okay,
No,
the test part.
yeah, it's because well, I mean, like unless I'm thinking wrong, a case where R is that R being 1 means a number like there's a 2, 3, right? That's what R being 1, right? And then so potentially R could be N, right?
Yes, R can all the way be all the way to N, in which case you should only have 2 possible. You should have N possible cases, or N times 2, because remember you have ascending and descending as well. So you can go clockwise or counterclockwise, but then you can shift the numbers by position. So you have 1, 2, 3, 4, 5, 6, and then you can have 1, 2, 3, 4, 5, 6, and shift it only by 1 position. So there are 6 possible ways to position the 1, and then for each time you have a 1 at each position, there are 2 ways to count it, because you can go counterclockwise or you can go clockwise. So when R and N are exactly the same, we kind of know what the answer is supposed to be, because it's just 2n divided by n factorial. It's the other ones that we need to kind of really work hard to find out.
Yeah, and if your N is large, then you basically are going to have to do R test cases.
Correct. But once you figure out the pattern, I think you will get to the general format pretty quickly. Okay. So the next thing I want to do is to kind of show you what kind of what is the size of the problem when you do everything by using a program. So we just want to look at the factorial of certain numbers. So I think it's factorial. Nope, it's factor. Nope. Fact. There we go. Because it doesn't use the entire name factorial. It's just fact. The factorial of 8 is 40,000 something. So if you do it by program, this is easily manageable. So I would definitely encourage people to test up to n equals to 8, because n equals to 3, 2, and 1 are trivial, useless. So you need to work with at least 4. But 4 you can do it by hand. 5 you cannot do it by hand, really, because you have 120 cases. But if you use a program, working up to n equals to 8 should not be a big problem. Okay. How would you do the generate part? This is the next question. How do you write this program to generate all the possible patterns? What do you need to do?
Just like what P is.
Sorry? Okay, so the first part of the program is really just generating these patterns, right? So the question now is, how do you write a program to generate these patterns? If you use C++, you're a little bit better off, because C++ has a template class called
Double linked list?
No. You need that concept. Okay, I'll give you the pseudocode that may work in this case. Okay, so I'm with emphasis on may. All right. So what you do is you basically you start with a set of numbers. Okay, so you just say the set is x here, and we'll just initialize x to 1, 2, 3, 4, 5. Okay, so we're working with the case when n equals to 5. So what you need to do is to say, okay, but how do we generate all the possible cases? Okay, so what you do is you write a subroutine like this one here. Okay, so I'm going to say this is all pseudocode. It definitely won't compile in any compiler. Okay, so subroutine generate. It will require a set. Okay, so I will say it will require a set. We'll call that parameter p. Okay, or p1. That's it. That's all we need. So this is definitely pseudo C code. I'm borrowing some elements from certain languages and some elements from other languages. Okay, so inside what you need to do is to do something like this. So you say for each element E in P1, do the following, and for. Okay? Such a thing does not exist in C or C++, so forget it. This won't work in C or C++. Although in C++ there are certain things that come pretty darn close to what we need here. Okay, I'm not going to name that particular template class. All right, so what you do with each element E in P1 is to do it like this. Okay, so you want to say, I think we need a second parameter. So we need a tuple T, okay? All right, so we need a tuple T here. So what we do is we basically, well, I think we can do it recursively. Okay, we need a conditional statement here. I'm sorry, if you're writing this down by hand, you'll just kind of not write anything until I'm done with this, because I'm actually coming up with the algorithm as we speak. So we say if P1 is not empty, then we do this. Okay. Or if you prefer, we can do it much more consistently and just use and if, else, and if. There we go. So the last case, the else case, is when P1 is actually empty, because it's the else branch of the condition when P1 is not empty. So when P1 is empty, which means we are done with selecting all the elements, which also means the tuple is fully built at this point. So you can, at this point, you can just say print the tuple T as the output. Which also means, if we are, in this case, when P1 is not empty, then what are we going to do? We'll do two things. We will add E to the tuple E. We'll also subtract the set of E from P1, and then we'll do it recursively. Okay, so we will do this recursively. We say gen again, which is recursion. So the first parameter is going to be based on P1, but not exactly P1 itself, because you have one fewer elements at this point. So you have to remember to take the element E from P1 when you pass it recursively as a parameter to the next invocation of gen. Okay, but the same token applies to E in the context of T, which is a tuple, right? So the tuple T needs to have E appended to it. So you basically have to look at the result of appending element E to the end of T as a tuple and pass that along to the next invocation. Yep.
Wouldn't you, after the do, wouldn't you be appending E inside that tuple? Like, wouldn't the process of taking out the element and calculating its series, wouldn't you just want to automatically put that back into it? I'm saying so
I'm not changing T itself. I'm only appending E to T and then sending a copy with the concatenation as a parameter to the next invocation. So this line here, let me just highlight which one I'm talking about. So this line does not make any changes to P1 nor T. P1 is not changed, but I am passing a new set, which is based on P1, but without the element E as a parameter to the next invocation of gen. And then the second parameter is kind of the same thing. I'm not changing tuple T itself. I'm making a new tuple based on T, but with E at the very end. So these are all passed by value. Are there any questions about the pseudocode? So how do you call this? Right, in the main program, the way you call this, so in main, okay, so the way you call this, assuming X is already initialized like this, so I'm going to copy and paste it over here. well, I don't even need to use a variable x for this purpose. I can just say gen, and then the first parameter is the set of all the numbers to begin with, and then the initial tuple is going to be an empty tuple because I have not chosen anything yet. So this particular recursive subroutine will generate all the possible combinations, or I should say permutations, of 1, 2, 3, 4, 5. But it does rely heavily on the concept of set operations, okay? Because you have to be able to enumerate all the elements in a set and be able to implement the subtraction of a set from another set, which is not native to C++, but the use of a particular template class can be very helpful. Yep.
Would you be able to, just for vision, what does one tuples look like?
Huh?
What does one of the tuples look like? Is it just that?
A tuple is just like this. It's just basically a list, or you can consider that to be an array. Is that okay? Yep.
So just to say that we got all the generating parts to work, what would be the parameters for like testing the generations themselves? Is my second question, I guess. 'Cause
Okay, so when you test, you have to test with the different r's, right? So when r equals to 1, it is trivial. Because what are the chances that you will have a certain way of assigning the numbers where you can find a sequence of 1 within a circle? It's 100%.
Oh yeah.
Because a sequence of 1 is just one number. Okay? Is that making any sense?
Yeah.
And we already just talked about the chances of when r equals to n, because that has to be a complete sequence. But you can shift the start position, and as a result, you have n way of going in one direction, and then you have n ways of going in the opposite direction, because it can be increasing, can also be decreasing as well. So we know that it's 2n divided by n factorial in the case of r equals to n. It's the ones in between that are kind of tricky. Okay? And then you have to think about, is there such a thing called n minus 1? But what happens when r equals to n minus 1? So you have at least n minus 1 elements that are or at least n minus 1 items in the circle that are in sequence. What about the one that is not in sequence? Can you have n minus 1 items in sequence and only one that is not in sequence?
No, because it would mean you would have to like start it at or something.
Okay, so kind of think about that. Okay, you guys have to kind of put some thoughts into it. But when you test everything using a program, it will make it very clear. So that's why I want you guys to kind of spend some time to write a little program, generate, and then do the test. Okay. Are there any questions about this particular code here? Now, since I'm not collecting the program itself, you don't have to do it in C or C++. If you want to do it in, I don't know, Scratch, okay? You can do it in Scratch. Scratch actually supports recursion, so you can actually do it in Scratch. And you can even have an animation of the cat running around. And this is not a challenge, okay? So don't waste your time if you say, okay, I can see that tech is challenging me.
I got this.
All right. Any other questions about how to get started with this particular homework assignment? No questions? All right. So if there are no questions about this one, we are going to move on to the next topic. The next topic is discrete probability distribution. So this time we are talking about one very specific distribution is the binomial distribution of probability. It is discrete, but yet it is also it's easy to model. Okay, there's a lot of math behind it. Do you guys remember what I asked you guys to do kind of informally? It's not a homework assignment, but I want you guys to think about if you toss a coin 5 times, what are the chances that you end up with 2 heads or yeah. Mm-hmm. So did anyone try to think about that one and come up with an answer? that's okay. So we'll go ahead and actually try to enumerate all the possible ways. Okay, we toss the coin 5 times, and we'll count how many times you can come up with heads up. Okay. So the 5 ways to do, or the ways to do this is the head is the first one. Okay. So head, tail, 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 head, head, tail, tail, head, tail, head, tail, head, tail, tail, head, head, tail, tail, tail. Okay. So these are definitely 4 ways of arranging this. And then I put a tail as the first one. Then I do the same thing. Head. Well, okay, this is not very systematic. Tail, head, tail, head, tail, tail, head, tail, tail, head. Okay? So this exhausts everything that can start a head as the second toss, right? So now we have tail, tail, and then we have head, head, tail, head, tail, head, and that should be it. Okay? And then the last one, there's only one choice because I have 3 tails to begin with, then I can only have 2 heads to end it with. Okay? So when you look at these numbers, what is that number here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So there are 10 ways to arrange this. But doesn't this kind of suggest something related to x plus 1 to the power of 5? Do you see any relationship between these two problems? Trying to figure out the number of heads in 5 tosses of a coin, as opposed to x plus 1, to the power of 5. How would these things relate to each other? Think of it this way. This is my head. This is my tail. So I'm trying to figure out the coefficient of which term? Okay. 2 heads. So that means I'm trying to figure out what is the multiplier of x squared in the outcome of the actual x plus 1 to the power of 5. Is that making any sense? Sort of? No?
Can you repeat that one?
Okay. So think about it this way. X plus 1 times x plus 1 times x plus 1 times x plus 1 times x plus 1. Okay? I'm not going to expand the whole thing out. Okay? But I can guarantee you one thing. It's going to have a certain number of x to the power of 5. Okay? In fact, there should be exactly 1. We kind of know that. And it has a certain number of x to the power of 4.
6.
And
Isn't it? Isn't it one of those?
Five of these.
Okay.
And so we know exactly this. There are 5 of these, 1 of these. Then we have a certain number of x to the power of 3.
This is just Pascal.
Yeah.
Yes, it is. But that's also what we are trying to do as well. Because how do we end up with these numbers? It's the way of arranging who gets to multiply to x and who gets to multiply to 1. Is that making any sense? Okay. So there's a certain number of x squared, and then there's a certain number of x, and then there's a constant at the end. We know this constant already, don't we? Because this is 1 times 1 times 1 times 1 times 1, and then there's only one way of doing it. So this is just exactly 1. How many x's do we get?
1.
No. Because there's 1 times 1 times 1 times 1 times x. There's 1 times x times 1 times 1 times 1. There's 1 times 1 times x times 1 times 1. There's 1 times 1 times 1 times 1 times x. And I think I'm missing one of those. But anyway, but that's why we have 5 of these, right? Okay? What about these two? The ones in the middle. It's kind of like, how do we figure it out? 10 and 10. Okay, so you can see the relationship, right? But you also know this one from Pascal's triangle, don't you? Okay, Pascal's triangle is easy. It's just 1, 1, 1, 1, 2, 1. So the edges are always going to be 1. But inside, you're basically just summing the 2 numbers on the top row. So 1 plus 2 is 3. and then we have 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, and so on. This is Pascal's triangle. But each one, these numbers are very important because each one tells you how we can calculate the numbers of coin tosses or the chances of coin tosses where you have a certain number of heads and a certain number of tails. Yep.
I see where you're going with this. Can you repeat the question you originally asked for them? What was the probability of how many?
The original question is, what is the probability of having exactly 2 heads out of 5 tosses of the same coin?
Since x is the h, we assume to the second power.
So we know there are 10 possible things, right? So 10, but 10 out of how many? In other words, with 5 coin tosses, okay, what is the total number of possible ways of arranging the heads and tails? Remember, each toss is independent from the previous one. So the first toss can be a head or a tail, 2 possibilities. The second toss can also be a head or tail, but that is independent to the first toss. So out of the first 2 tosses, there are 4 possibilities. The third toss is independent to the first 2, so that means out of 3 tosses, there are 8 possibilities. So out of 5 tosses, how many possibilities do we have? 2 to the power of 5, which is 32. This is your probability. This is your chances. Because you are looking at the frequency of individual items that you are interested in and divided by the total number of possibilities that you can end up with in this case, 5 coin tosses. Is that okay? Yep.
I was just wondering, why did you actually expand the equation again, the x plus 1
Oh, yeah.
and the x plus 1?
So we got
What was the reason behind doing that?
Because the reason why you get 10x cubed is because there are exactly 10 ways to combine out of these 5 x plus 1s.
Right.
There are exactly 10 ways to pick 3x and 2 1s.
Oh,
Because
I
that's
see.
the only way you can end up with an x squared. I mean x cubed. But that's also related to the problem that we had originally. It's just that, in mathematics, we kind of look at it slightly differently. Yep.
So, in that case, that 32 is, so if we have another problem like this,
Mm-hmm.
the total number of possibilities, that denominator, is just gonna be like, the sum of some one of Pascal's rules.
Right, but this is actually the cardinality of omega, which is the total number of outcomes, whereas the numerator is the cardinality of it's the size of the event itself, which is basically an event is a set of outcomes that we are interested in. In this case, the event is called having 2 heads out of 5 coin tosses, but that event has exactly 10 outcomes as its own elements. So that's why we are dividing 10 by 32. That will give you the chances. So we have about 1/3 of a chance of getting exactly 2 heads up out of 5 coin tosses, which is exactly the same of the chance as the chances of getting 2 tails out of 5 coin tosses, which makes sense because it is symmetric. Is this okay so far? Yep.
How did you know? How did you figure out that you needed to use x plus 1 to the 5th power?
Well, this is called the binomial distribution.
No, but how, out of the flips and everything, how did you get that x plus 1 to the 5th power?
That's what he's saying, the x plus 1 is the
Because the x is
I
kind of
know,
like
it's okay.
head, and then the 1 is kind of like tail.
So that's
by
not how you
looking-
thought of it.
Yeah,
Like, how'd you think of it?
Where
I
did you,
guess
how
is
did you just,
question.
come out with that number?
Just, hey, check out this thing that you wouldn't
Yeah.
think is anything like that unless you.
Because this number, because the coefficient of x cubed is going to tell you exactly how many ways you can combine exactly 3x out of the 5 and only 2 1s out of the 5. So I just renamed the things. X is head and 1 is tail. but we are trying to figure out exactly the same thing. But the reason why I relate to this one is because most people already know Pascal's triangle for figuring out the coefficient of something like this. So I'm trying to relate something that you already know, or most of you already know, which is this thing, to solve a problem that seems to be a new problem, but it's not a new problem. It is an old problem that you already know how to solve. Yeah.
But a few lines above, you asked us what the coefficient of x squared is. Now, in this particular instance, the coefficient is still 10.
Yes.
But why do you have 10x cubed circled if you want two x's, which is two heads?
Well, I mean, it's only a question of which one is the head, which one is the tail. You can look at one as the head. You can look at x as the head. The other one is going to be the tail.
Right, but before you spelled it out, you assign h to your x.
Oh, okay. So that means I should be looking at x squared, which basically
Well, you said
has the same
having
number.
3 heads,
Yeah.
whatever
Yeah.
is the same thing as that.
Yeah, but it's the rationale that is important. I kind of flipped the sign, okay, as I was talking about. But are there any questions about how the Pascal's triangle is actually solving this problem, which doesn't seem to have anything to do with binomial?
So, what if instead of a coin we had, say, a 3-sided die, and we're looking for everyone that comes up with 2 1s? When instead of our x plus 1, which is only going to deal with 2 variables.
How do you make a 3-sided die?
I've seen them.
It's a small little pyramid. The points are
No, that's a
actually
4-sided die.
Yeah, because you cannot have a
Okay, so
3.
4-sided.
No, but it looks like a.
The point being that
It
you have 3
exists.
variables.
Okay. So that would make it a little bit more complicated because the combinations get a little bit. There are more combinations. This is the one where people are more interested in because it's either yes or no because it's binary. And as a result, when you look at the distribution, if you continue with the Pascal's triangle and you work your way up down to maybe 20 or 30, okay, and you plot it out, what does it look like? Has anyone tried that with the Pascal's triangle? It will start to smooth out because when you look at the first few ones, it's really kind of jagged, right? 1, 2, 1, right? And then the next one, okay, let's look at 1, 5, 10, 10, 1. So the shape is going to look like 1, 5, 10, 10, 5, 1, okay? But as you work your way down on Pascal's triangle, it will start to look more and more like the normal curve, okay, which is a continuous distribution. But it does look like the normal curve because it smooths out, okay, but the shape is there, okay? So that's why the binomial distribution also has significance because as n increases, it will start to approach the normal curve. Okay. Any other questions? Well, okay, so yeah, go ahead.
So, does the number 10, is that the cardinality of the F letter?
Well, depends on what you're interested in. Now, it is not the cardinality of the funny F. It's the cardinality of an element of the funny F. The funny F is a set of all the events you want to figure out. But each event is a set of outcomes. And each outcome is just one way that things can turn out. Any other questions? Well, I have this really important question.
What is it?
Instead of working my Pascal's triangle, which is fun and graphical and visual and all that, but it seems like it's going to be a problem if I try to figure out of 40 tosses, okay, what are the chances that I end up with 5 heads and 35 tails? Because that will require me to work my Pascal's triangle all the way down, which is a problem. Okay, 40 may not be a problem, but about 400. So at some point, you don't want to work out the Pascal's triangle anymore. So the question now is there a closed form to express this 10? Is there a closed form to express this 5? And so on, okay? So before we try to randomly plug equations or formulas in and see which one fits, let's think about another way to denote or encode this thing here, okay? One way to encode this is really just to have a set of numbers to denote the positioning of the heads. Okay, but that's one way to indicate, this particular way of arranging the tosses, right? So this one can be encoded as 1, 5, because the first and the last tosses end up with a head. Is that okay? Sure. The second one is just 1, 4, 1, 3, 1, 2, and then we have 2, 3, and then we have 2, 4. I mean, you know the pattern already, right? 2, 5, 3, 4, 3, 5, and then eventually we have 4, 5. 4, 5. There we go. Okay? How is that helpful? Isn't this the number of combinations of picking 2 things out of 5? We have 5 numbers, 1, 2, 3, 4, 5, and I just want to pick 2 things out of those 5, and I'm just counting how many ways can I pick 2 items out of 5 where sequencing or ordering is not important. But we have a closed form, we have something to denote that already, don't we? It's the C notation, C5, 2, which is 5 choose 2, seems to be doing the same kind of calculation as what we did by just manually counting or using Pascal's triangle to figure out this 10. So now the question is C5, 2 exactly 10? That becomes the next question. In other words, we have 5 factorial divided by 3 factorial times 2 factorial. Is that, okay, equals to, is that 10? 5 factorial is 120. 3 factorial is 6. 2 factorial is 2. So we have
12 divided by 12.
Yep, it is exactly 10. So we do have a closed form or closed formula for these coefficients. Okay? Is that okay so far?
So in the case, our R becomes the power on the X. And our N is just the number of.
Yep. So you can in other words you can look at it this way. You can say if we have x plus 1 to the power of n, okay, when you express this, and break it out into individual parts, it becomes a summation of individual powers of x, right? So that power, is going to using I as an iterator. So I should iterate from 0 to n because we have x to the power of 0, which is just 1. So now we can basically say, okay, so how many of x to the power of I do I have when I expand out x plus 1, the whole thing to the power of n? So now this part is just n choose I.
But wasn't that form for P? Isn't that how we wrote P?
Huh?
Isn't that how we also wrote P though? So where the order, the permutation where their order
Yes.
wasn't ordered?
Yep.
Okay.
No. This is C, not P.
It's not, okay.
This is C. This is the combination, not P. P is permutation. Yep. Yep.
Can you say that formula one more time?
Okay, so this is the summation sign, which means we are looking at each individual item, and the value of the entire expression is the sum of all the individual terms. What about each individual term? You can see that I is a parameter of each term, and I goes from 0 to n. So this is basically saying if I want to figure out how many units of one, or what is the constant, it really is just n choose 0. But n choose 0 is known to be 1. Is that okay? And then n choose 1 is n choose 2 is some other value, and so on. So instead of using Pascal's triangle to figure out the coefficients, I can now use something that we already know, which is combination, to figure out the coefficients of each power of x when we expand x plus 1 to the power of n.
Okay, so x to the I that's the coefficient of x to the I.
Correct.
Okay.
So when you expand this out, okay, or you can just kind of look at a few terms. So the first term is going to be n choose 0 times x to the power of 0. And then the next term is going to be n choose 1 times x to the power of 1 plus n choose 2 times x to the power of 2, and so on. Is that okay so far? This class does look like a math class now, doesn't it? But wait, there's more. Okay, so this is called Pascal's identity. There are two links to Pascal's identity. One is an outside link, and the other one is something that I actually typed. They are slightly different. Okay, they're proving the same theorem, but I did it in a slightly different way from this particular way. Okay, so what we want to focus here is the theorem itself. Okay, it has its own proof. So the theorem is really just this part here. The theorem states that n choose k is the same thing as n minus 1 choose k minus 1 plus n minus 1 choose k. Now, why is that important? Have we seen something like that on the whiteboard already? And it is in the form of see, now I can start to understand why the math professors like the whiteboard. But it is still on the whiteboard, okay? So look at this equation here, okay? Assuming this theorem is true, which part of the whiteboard is it relating to? Look at n as the row number and k as the position of a row. What is this mapping to on the whiteboard?
Triangle.
The Pascal's triangle, exactly. So when you look at this equation and you say, okay, the top number in the parentheses is controlling the row number, and then the number at the bottom is controlling the position of the row, that is exactly how we come up with Pascal's triangle. Is that okay or not? All right. So the question now is, well, according to Pascal's triangle, it works, okay? But can we prove mathematically that this works? Because you cannot use Pascal's triangle to say that, okay, in general, the theorem is true, because there's always the next row that you do not know whether it works or not. But by the time you work on the next row, what about the row after that? That may not work anymore. So you want to be able to prove this mathematically and not just numerically or empirically, just using numbers. So this one is just one way to prove it. If you read the rest of this link here, it is just one way to prove it. So it says right here, if k is greater than n, then n choose k is 0, which is also the same thing as n minus 1 choose k minus 1, because in that case, k n minus 1 is also going to be less than k minus 1, so it's a trivial case. So we basically usually just assume k is less than or equal to n, because otherwise it doesn't really make a whole lot of sense. So this is the proof. Let's see if we can go through this line by line and understand this proof. Okay. Okay, are you guys ready for this? I know it's kind of late in the day. This is not heavy-duty math. It's just a little bit different from your usual math because it involves factorial. Factorial does all kinds of cool things when in a proof. Okay, so the first part, or the first line here, is just expanding the parentheses into factorial operation. N minus 1 choose k minus 1 is n minus 1 on top, k minus 1 by itself on one side, and then this one is really just coming from n minus 1 minus k minus 1, okay, with parentheses, okay? So that's how we come up with this term here, and this term we come up with this term basically exactly the same way. It's just by the definition of combination. Okay. Are there any questions about the first row of the proof? How did we go from the first row to the second row? Okay, that's a pretty easy one. Just factoring. Yeah, exactly. Because each one has the same numerator, so we extract the numerator out, so it's outside, and then we have the rest, being inside. But wait, hold on a second here. We also did something to the inside, because the inside should have been 1 over k minus 1 factorial n minus k factorial. So how did we come up with this k up here and this k n minus k up here? That has to do with factorial. Okay. So when you look at the denominator of each term, okay, so let me just point out which one I'm looking at right here. So look at this term here, k minus 1 factorial times n minus k factorial, and then look at this entire term here. What is the difference? There's only one minor difference, right? Because this one only works up to k minus 1. In other words, this term here, I cannot select, I cannot highlight it. But this term here is 1 times 2 times 3 all the way up to k minus 1. This one is 1 times 2 times 3 all the way up to k. So there's only one difference, okay? The term k itself is missing from this one. But it is present on the other side. So what we do is we introduce the k in the numerator to cancel it out. Is that okay or not? Sorry? Is that okay? I mean, does everybody see how we went from the first row to the second row? So factoring is the easy one, okay? But the second step is to make use of factorial by introducing k, adding k to k minus 1 factorial. We end up with k factorial. But we need a k in the numerator to cancel it out because it wasn't there in the first place. Okay. How many people want me to kind of spell this one out a little bit more? Okay, very good. Okay, so the question is, how did we go from 1 over k minus 1 factorial? Let's just focus on one term, okay? How is this the same thing as k over k factorial? Why? Well, okay, so what we do is 1 divided by k minus 1 factorial. Can I multiply 1 to this whole thing?
Yes.
Okay. Can I write the 1 as k over k?
Yes.
Is that okay? All right. What is k times k minus 1 factorial? It becomes k factorial, right? That's how we can prove that step. Is that okay? So this is really just explaining why the denominator here becomes this denominator, but we also have a numerator of k. Is that okay? So as I said a little bit earlier, this is basically your typical usual algebra thing, except the factorial makes certain things kind of possible, because you can extend a factorial. The same thing happens to the other side. Okay, on this side, the original thing has a denominator of k factorial times n minus k minus 1 factorial. It becomes n minus k factorial because we just added one term. It's basically the same principle as what we have here. Is that okay? So are we okay with the second row at this point? It's just a technique. Okay. All right. So from the second row, how did we get to the third row? I mean, that one is pretty easy. Yep, so we just combine them because when you look at 1 over k factorial times n minus k factorial as a factor, then we can combine the numerators. So when you combine the numerators, it becomes k plus, and then in parentheses n minus k, so the k and the minus k cancel out, then you just have the n left. Is that okay? So that one is really just kind of usual algebra. So now we end up with, we go from the third row to the fourth row, going from this row to this row here. So how did we end up with just n factorial? Because n times n minus 1 factorial is n factorial. So once again, it's using the same trick again, okay, just to go from the third row to the fourth row. But when you look at the fourth row, by definition, it is also known as n choose k, because it is n factorial divided by k factorial and n minus k factorial. So that's the proof of why Pascal's triangle works. Yep.
When you say n choose k, what do you mean by that?
N choose k.
I just didn't know what that meant.
Okay. It's just, that's how we call that.
Okay.
Yep. So there are some alternative proofs here. But let's go back to my own notes here, because I have my own proof. This is my own. Mine is a little bit longer because it spells out all the items. Okay, so let's look at this one, which seems to be a little bit longer. So the way I did it is to use n choose k plus n choose k minus 1, which is just one step to just the next step, but it works out pretty much the same way. Okay, so this is the first row is by definition, and then the second row is by moving the parentheses a little bit. Okay, can everybody see how I went from the first row to the second row, which is actually the only thing that was changed is this part here. And then from the second row to the third row, I introduced a k here. So k minus 1 factorial becomes k factorial. That's how we that's how we got from second to the third row. And then from the third row to the fourth row, I took one term out of n minus k plus 1 factorial and put it here. Okay, I'm just rearranging things a little bit. Okay, and then I did the same thing to the other side. So I just move one term, which is n minus k plus 1, out of this factorial and put it up here. Is that okay? It's the same term. Okay, if you look at this, this is the same term as this one here. So I'm not changing the value because it's really the same term. But then after that, the denominator, they become the same. So I have the same denominator. I can now combine the numerator. So the numerator becomes this part, and then we. Okay, so how do we do this? Oh, okay. So I move this denominator into the common denominator, and because of that, we can now have n minus k factorial times n minus k plus 1. So the whole thing becomes n minus k plus 1 factorial. The top becomes just n plus 1 factorial because these two terms cancel out. And then from this one to this one, let's see, what did I do? Oh, I changed the ordering. So instead of saying n minus k plus 1, I changed so that it is n plus 1, the whole thing, minus k. Is using the, just moving the components around. But by definition, n plus 1 factorial over k factorial times n plus 1 minus k factorial is also known as n plus 1 choose k. So it's kind of the same thing, I just chose to do it in a slightly different way, moving things around a little bit differently. So are there any questions about this particular proof? Or, this is mechanical, which is the how, okay? Okay, so the how is basically all kinds of little tricks that we can do with factorial. Okay, we can take one term out and do some funky stuff with it. That's the how. What did we talk about? What is that? Some gibberish math stuff. It's Pascal's identity. Okay, but what is Pascal's identity? It's it goes back to the definition, right? The theorem itself. In the end, all we're trying to prove is this. So now we move the question up one level. Why is this important? because your degree requires you to get a C out of cisp440. No, because this is why Pascal's triangle works. Because this explains why we can do this, okay? 1 plus 4 is 5, and 4 plus 6 is 10. This is how we can come up with the next row, and then the next row, and then the next row. So if you take this one level up, just one more level, why did you study Pascal's triangle in your other math class? Which math class is that, by the way?
Algebra 2.
Algebra 2? Okay. So why is Pascal's triangle important?
For when you got some more polynomials to n.
Exactly. Yep. And why is that important?
Because functions can go on forever.
Because you could use that to approximate logarithms and break it up into terms.
Yep. Well, also because it's just useful algebra to begin with. Yep.
Yeah.
All right. So is that okay so far? Pascal's triangle or the proof of Pascal's triangle. Okay. So let's move on to the next slide.
Okay.
Oh, sorry.
I don't think it has anything to do with that. But what would be like the sigma notation if you wanted, like what you wrote there, where your fingers go down, right there. So that's going to give us the coefficient for the I.
X to the power of I.
Yeah, right. Now, if we wanted the sum of the nth Pascal row, how would we write it with that basically?
It's the same thing. Okay, so if I understand your question correctly, you want a closed form of the nth row in Pascal's triangle. Oh, you want the sum of that?
Yeah, because so that's
the sum of that is really just all this stuff without x to the power of I.
But you just run all the way to n.
Yeah, because these are the coefficients, right? Which are basically the numbers on each row. So if you take out x to the power of I, you're just adding all the coefficients. But that is also interesting, because if you add up all the coefficients, what do you get? You always end up with a power of 2. Yeah. But isn't that kind of interesting? I mean, it's not coincidence either, okay? So when you look at this term here, okay, this pen is fading. So when you look at this term, I goes from 0 to n, and really just n choose I without the x to the power of I component.
Yeah.
This is the same thing as 2 to the power of what?
I. No,
N. I cannot be the case because I is an iterator, so I goes away when the left-hand side is evaluated.
And I goes to n.
But this is 2 to the power of n. So you can now see a kind of weird combination because, hey, looks like combinations has something to do with the power of 2 also. Well, it kind of does, okay? Are there any questions about all of this stuff here?
Yeah, what's the kind of?
Ultimately it relates to set theory, whether something is there or not. Yeah, and that's why there's a 2 to the power of something. 2 means 2 states. Is it there or not? N refers to the number of elements. All right. Any other questions? Are we ready for more math stuff? Well, we have another theorem that we have to prove. I think this one, is already kind of pretty clearly stated. Okay, that's basically what I wrote here on the board already, early on in the class. Okay, which is this part here. That one just has a quantifier that says for all n as a natural number, this theorem is true. Okay. Well, it kind of makes sense because according to Pascal's triangle, it makes sense. According to Pascal's identity, we just proved it, so it makes sense. But how can we prove this directly? That 1 plus x, the whole thing to the power of n, is the summation of n choose I times x to the power of I. Okay. So this is where we introduce a new proof technique. The new technique that we are proving something is called proof by induction. Okay, proof by induction is interesting because it relates to something that you might have learned in some of your other classes, which is recursion. Okay, so recursion and proof by induction are very closely related. One is a coding technique, the other one is a proof technique, but ultimately these two are closely related. So let's take a look at proof by induction. What does it mean by proof by induction? Proof by induction requires what we call a base case, which is a single case that is proven to be true without anything else. So you can establish that the base case is always true. When n equals to 0, this is always true. Okay, so that's the base case, which is the same thing as the condition where recursion stops. Okay? That's basically our base case. The step is basically saying if the theorem is true for case n minus 1, then it should also be true for case n. In fact, the proof of quote-unquote the step is really just to prove from case n minus 1 to n. And that's induction. This is called the induction step. In other words, it's basically saying if you can show me that this theorem is true for case n, then I only have to prove why it will also be true for case n plus 1, then I have completed my proof already. Now that's a really powerful proof technique because you don't have to prove for each individual case. Okay, you just need a base case and the induction step. Let's not work with something this complicated because we probably won't have enough time. Let's think of I don't know whether factorial is something that we can do. We can do this because factorial can be anything that can be defined recursively can easily be proven using proof by induction. So I just need to think of something that is recursive, and factorial is recursive. But I need to find a property of factorial to prove, because otherwise, there's nothing to say about factorial. I know. Okay. Squares. That may not work.
The Taylor series? The Taylor series?
No, I don't remember anything about the Taylor series.
Good. That's good.
That's like 20 years ago. The last time I touched the Taylor series was 20 years ago. Let's see. Proof by induction. That's not the closed form that I want to kind of. No, this is the expanded version. This can be done by just algebra. You don't need proof by induction to do this. But there is a way to do x plus 1 squared, recursively. So I just need to think of how to do that.
When you're using limits to prove something, isn't that the same thing as proof by induction?
No, limits is different because limits is basically just proving the behavior of a value asymptotically. This is not asymptotic at all. Things do not need to converge or diverge. You're just saying, okay, if the theorem is true for case I, and you can prove it is true for case I plus 1, then you have just proven it for all the cases.
Certainly is a better multiplication.
Oh, okay, maybe this. Okay, the summation of I going from 1 to n. How about this? Okay, we already know the answer to this one, don't we? Because it should be something divided by 2. What is it? I think it's n times n minus 1 divided by 2, or n plus 1 divided by 2. Okay, let's just, I just need to figure out it quickly. 1 plus 2 plus 3. Okay, so when n equals to 3, it is 6. So 3 times 2, okay, so it is the minus 1. It's the little things that I cannot remember. Okay, so I think that No, is it? No, it's n plus 1.
Like, isn't this what we did with the when we were doing that little triangle? Yeah, when we do that space.
Yeah, but I want to do this using proof by induction. Okay, so I just need to make sure that this is actually true. Okay, 1 plus 2 plus 3 is 6. 3 times 4 divided by 2 is also 6. Okay, so that works. Okay, so we want to prove this. We want to do this by proof by induction. Okay, so when you do this by proof by induction, you need a base case. So the base case in this case is which one does not require any actual proof? When n equals 1, right?
We don't have 0.
Because when n equals 1, we have I going from 1 to 1, which is 1. But can we prove this is the same thing as 1 times 1 plus 1 divided by 2? Yeah, we can do that. Cool. Okay, we have our base case. Then we look at the induction step. Now the induction step is a condition, okay? It is an implication. We have to prove an implication. The implication is basically saying if this is true up to k, for some k, this is I equals to k plus 1 divided by 2, then the following has to be true. Then this should equal to k plus 1 times k plus 2, because it's k plus 1 plus 1, so I combine the plus 1 to 2, divided by 2. Okay? So the question is, can we go from here to here? Okay? So how would you do this?
Multiply it out?
Okay, multiplying out would be helpful. Okay, so let's multiply out this side first. Okay, so we have k squared plus 3k plus 2, right? And then the whole thing divided by 2. So what you want to do is to find this thing within this thing here. Now this thing here is just your k squared plus k divided by 2. Is that right? Okay. So now you chop up this term here. It becomes your k squared plus k. Group that into 1. The remaining part, which is 2k plus 2, you group them separately. The whole thing divided by 2. Is that okay? And then you take this part out and say, hey, that really is the same thing as this thing, right? What about the other side? 2k plus 2 divided by 2 is k plus 1. Okay, it's just k plus 1 here. So now the question is, can we show that this is the same thing as that? Yeah, because the summation of I going from 1 to k plus 1, I being the term, is the same thing as going to k only, but adding the k plus 1 term separately. So that's how you can establish the induction step. But once the induction step is done and the base case is done, I'm done with the whole proof. But Tech, are you really sure this will work when n equals to 3026? Yes. Why? Because I can show that it is also true for 3000 and what? 26. So by proof by induction, I can prove it is true for 1, but by induction, it is also going to be true for 2, 3, 4, 5, and then we can go all the way to whatever number you want. So that is the whole nature of proof by induction. You just need to establish the base case and just say that yes, you can take a step up from any other step. Then you can establish that it's going to be true no matter how many steps you take. Is that okay so far? I did not plan to use this particular proof as an example of proof by induction, so you might be a little bit rusty, but so I had to spray some Rust-Nonium. All right, so we are done with today's class. So next time we will get started with that one, with that particular proof, which is the binomial theorem. What's the other?